All right, let's just dive right into this explainer. Today, we're going to demystify something that is absolutely foundational in mechanical engineering and the plant industry, and that's operating pressure. Whether you're designing massive chemical plants for an EPC, an engineering procurement and construction company, or you're just kind of curious about how these huge industrial systems don't just blow up, well, this is exactly where it all starts. So, to kick things off, I've got a question for you. What actually prevents a kitchen pressure cooker from just exploding right in your face when you're making dinner? No, seriously, think about it. That pot is trapping some incredibly hot steam, and it's building up a ton of intense energy. Well, the everyday engineering that keeps your own kitchen safe, it relies on the exact same principles that mechanical engineers use to design those massive, multi-ton industrial pressure vessels. And the real cornerstone of all that safety? It's understanding the normal state of the equipment. Now, if we look at the official standard, specifically ASME Section 8, Division 1, which pretty much governs pressure vessel design globally, they give us this, rather dense definition. It reads, operating pressure, the pressure at the top of a vessel at which it normally operates. It shall not exceed the maximum allowable working pressure, and it is usually kept at a suitable level below the setting of the pressure-relieving devices to prevent their frequent opening. Okay, wow, I know, that is a whole lot of intimidating engineering jargon. But hey, don't worry, we're going to break this down into plain English, piece by piece, until it makes absolute perfect sense.
All right. Rule 1. Measure at the top.
So let's pull apart that ASME definition a bit. Why do engineers specifically dictate that pressure has to be measured at the absolute top? Like, why not the middle or the bottom? Well, notice how a typical pressure vessel is laid out. You've got top nozzles in a manhole where the gas usually sits, right? And then compare that to the bottom nozzle outlets and structural saddles where heavy liquid just naturally pools. In a massive vertical vessel out there in a real plant, it is rarely completely empty or completely full of liquid. You've almost always got a mix. And this actually brings us to our first major engineering challenge. You see, the pressure at the bottom isn't just the ambient gas pressure of the system. It actually carries the physical, literal weight of all the liquid pushing down on it from above. In the industry, we call this static pressure. Think about it like scuba diving. When you dive into the ocean, the deeper you go, the more pressure you feel in your ears, right? Water is incredibly heavy. In a plant vessel, if you have roughly 10 meters of liquid water pooling at the bottom, that static weight adds roughly one entire bar of pressure to the bottom reading compared to what you'd read at the top. So the really crucial point here is that by always measuring at the top, engineers get a consistent, totally reliable baseline. This baseline purely reflects the gas pressure that's driving the process. It doesn't just constantly fluctuate every single time the liquid level rises or falls, and it isn't skewed by the physical shape or height of the vessel itself. It's just clean, simple, and standard. Moving on to Rule 2, stay below the MAWP. Now that we know exactly where to measure our pressure, let's talk about upper limits. MAWP stands for Maximum Allowable Working Pressure. Basically, think of MAWP as the absolute structural ceiling of your equipment. It is literally the maximum physical pressure the vessel can withstand in its current condition before you run a serious risk of structural failure. So it kind of goes without saying, but ASME says it anyway, just to be sure, your normal day-to-day operating pressure absolutely must be lower than the physical breaking point of the vessel. And that brings us to Rule 3, keep below relief setting. This third rule actually brings us right back to our kitchen pressure cooker analogy from earlier. Whether it's a home kitchen or a multi-billion-dollar oil refinery, safety codes strictly demand failsafes. So if an abnormal condition occurs, say an operator makes a tiny mistake or a valve just gets stuck, and the pressure suddenly spikes way past our normal operating limits, a mechanical relief device will automatically pop open. This safely vents all that excess pressure into the atmosphere or maybe a flare system, which entirely prevents a catastrophic explosion. But here is the catch, and it's perfectly captured in this quote from the code. Good plant design means keeping the normal operating pressure at a suitable level below that relief trigger. Why? Well, because you really don't want your massive industrial safety valves popping open constantly like a whistling tea kettle every single time there's a tiny little fluctuation in normal operations. Relief valves are meant for emergencies, not for daily venting. If your normal operating pressure is creeping too close to the relief setting, your plant is going to be an inefficient, noisy, and just constantly venting nightmare. So, let's wrap this up with the normal operating state. When a junior engineer steps into an EPC company on day one and looks at an equipment data sheet, they're going to see dozens of incredibly complex data points. But the operating pressure, that is truly the heartbeat of the system.
It simply represents the normal, stable operating state. Just remember our 3 decoded rules here. 1. We measure it at the top of the vessel to completely avoid the literal weight of the liquid. 2. We make sure it stays well beneath the MAWP, our structural ceiling. And 3. We keep it safely below the relief device setting so we aren't accidentally triggering emergency valves during our normal workday. And there you have it. That is operating pressure, completely demystified.
But, this leaves us with a really fascinating thread to pull on for next time. If operating pressure is merely our calm, normal, everyday state, what actually happens when engineers intentionally push a vessel to its absolute breaking point? How do we calculate the exact thickness of the steel required to survive those extreme conditions? Well, that enters the realm of design pressure and maximum allowable working pressure, which we are totally going to tackle in our next explainer. Until then, keep questioning how things work.